Hello, and welcome to the SciShow interview show, where we talk to interesting people about interesting stuff remotely through Skype. I'm in Missoula, and Tabetha Boyajian, did I say that right? Boyajian. You are in Louisiana, former researcher at Yale University, currently at LSU. And you've been working on maybe one of the weirdest things that has happened in astronomy research in a long time. Tell us about this weird thing.
I work on the science team as a part of the Planet Hunter Citizen Science Project, which is a part of the Zooniverse collaboration. What Planet Hunters does is an interface that shows data from NASA's Kepler mission to the public. And so, people can sign on and look for what we call transits in this data. The Kepler telescope measures a star's brightness versus time. And when a planet crosses in front of a star, then it blocks out a tiny bit of light, and you can see this in this data. And this is what the Planet Hunter researchers or citizen scientists were looking for. And the thing is, like, when you're going through all this data, you're looking at every single star and, what every single star does. And stars can do lots of things. They can pulsate, they can have flares, they can have spots, they can be a binary star, many different phenomena. But they came across this one star that didn't really fit into any classification that they had seen before, and they started talking about it and discussing it amongst themselves. It got to a point where they got stumped enough to reach out to the science team and say, hey, what's this?
Yeah. When we're looking at Kepler data, usually we're running, I assume, because it's so many stars and the vast majority of them aren't, nothing really of particular interest is going on. So I assume that we have computer programs that are trying to find specific patterns, and they're pulling those out and then later for direct analysis by scientists. But if it's not fitting that particular pattern, it's not necessarily getting pulled out by those programs and thus not even getting looked at. So is this citizen science group, the goal is to try and find some things that might not be noticed by computer programs?
Well, I mean, you're right about that. Computers do exactly what you tell them to do. And, especially with time series data, as simple as this, you would think that, a computer would be able to pull out, something as periodic as a planet in orbit transiting around a star.
Right.
And so that was kind of a gamble when we set up the Planet Hunters project, is that it was designed to look for transits, which computer programs were looking for the exact same thing.
Right.
But, we've actually found dozens and dozens that have been missed by the computer programs. And this has been able to inform the algorithms on, where they have, leaks in the pipeline. And so they can patch those up, and so it can be more and more efficient. But, again, as you said, you could also see, since people are viewing these data with their eyes, they can spot out something that you weren't actually looking for in the first place.
Yeah. So you guys noticed or somebody at Planet Hunters noticed a particularly weird looking signal, and that became a pretty big story. What is this star, and what did it look like?
Well, the Kepler data lasts for 4 years, and it took a brightness measurement of the star every 30 minutes. And what we see for most of the time, the star's light, or its light curve, is flat, meaning it's not really doing much of anything. But then it's punctuated in about a dozen places or so, and these drops in its brightness, these dips. And these dips are, they're unusual for this type of star. They're not periodic. Right. They're not symmetric. They last for enormous amounts of time and then go away for, years. And there's really nothing that says, oh, okay, well, this can be, associated with this phenomenon, or this can be, associated with that phenomenon. Yeah, and they were insanely deep as well. Right. These dips went down. Some of them were only, a percent or a fraction of a percent deep, and some were over 20% deep. Oh, wow. And so none of them looked like any of the other ones as well.
So are there sometimes planets that big that transit, or that close that transit? I guess a supermassive, hot Jupiter might create that kind of a dip.
So for this type of star, it's about 50% bigger than our sun. So a Jupiter, which it's theoretically as big as planets can get. If you put more mass into a Jupiter, then it will stay the same size.
Okay.
And so if Jupiter was, transiting the star, it would take over 50 Jupiters to make 20% drop in its light.
Okay. So basically what we're saying is like no one knows at all what's happening, and thus let's start just speculation excitedly.
Well, it didn't quite go like that. At first, I mean, this is scientific method. You know, like you have a problem, presented to you, and then you start collecting data to see if, anything will lead to, an obvious conclusion or something like that. So we started learning as much about the star as we could. But everything that we learned about the star made it look normal. Right. So, and that made it even more difficult to explain what was happening in the Kepler light curve. And so honestly, for years, I mean, this was kind of, being tossed back and forth, talking to dozens and dozens and dozens of astronomers, bouncing ideas off them, trying to, see, what we could test next, what theory we could test, all sorts of things were going on. And, honestly, there was nothing really, in our eyes, there was nothing really exciting about this at this time because we couldn't figure it out.
I mean, not knowing is always exciting.
Yes and no. I mean, now that I reflect back on it, I had two different feelings on it. Not knowing, that's why we love doing science. As a scientist, we get to say something new for the first time. But it's, at what point are you satisfied with, yay, I said something new, I accomplished this, project, I answered this question, tested this theory out, and I have an answer. But this one, it was, years into it, and it was kind of like, well, we really don't know. And so in that sense, it was frustrating, but then it was exciting because, wow, we don't know. So that's kind of cool too. Right.
And well, part of the frustration, I mean, for me, is that if you look at the data from this thing, it's in the middle of like this tremendous, very long period of time of the signal being dimmed that Kepler turns off. And I'm just like, oh, great, perfect timing. Could we just have fixed something to keep that going? Because like it does feel like the thing you need more than anything else is more data. And I know that this started as a citizen science project, and to get more data, that requires more funding. And it's interesting to me that you went for what I would consider a non-traditional route for finding that funding. Tell me about that.
Well, essentially what we did is we did a crowdfunding project through Kickstarter to raise money to get more data on this star. What this star needs is long-term monitoring, just watching it, every hour for the next 10 years, basically. And, it's a kind of high-risk, high-reward type project. And this isn't really viewed favorably in, say, the traditional funding routes as, something that, when you have a successful grant, it's typically something that's like, it's going to produce results. And this was something that was a little more risky. And so that didn't really seem to suit us. And any kind of public facilities that you can apply through NASA don't actually have the capabilities to do long-term monitoring. And so we actually had to go to a private observatory that does have the capabilities. It's the Las Cumbres Observatory. Is an array of telescopes around the world, and this can monitor the star continuously. So when it's nighttime in the U.S., it's daytime, halfway around the world. And the Kickstarter idea came up quite naturally because this star was discovered by citizen scientists. We thought we could continue on this theme and have people still contribute. A lot of people were interested in what was going on. And just, we could educate them as, to see, how science is kind of in action.
So we can actually, I mean, I imagine that it is not easy to sensitively measure the brightness of a star from Earth. I know that we can do it, but like to do it for the potential years that we need to get good data on this, because there, a large portion of Kepler's mission passed where there was just completely steady light coming from this star. Is that feasible? Is that happening? Is that like, are we going to see it?
Kepler was designed to catch transiting planets, so Earth-like planets transiting like a sun. And so Earth is 11 times smaller than Jupiter, and so like you would see like, I mean, it is such a fraction of a percent of light that it would take away from this. So there is, the analogy that, you have the Empire State Building and it's all lit up with lights, and you have somebody raise one of the blinds down by 1 inch, and this is the flux decrement that Kepler was designed to detect.
Right.
The signals that we're seeing in our star aren't that small. And so we don't need that kind of precision that Kepler gave us. Right. Kepler did have year-round coverage, and there's a period of about 2 to 3 months in the wintertime where we cannot monitor this star, which can't have everything. But, the precision that we can get from the ground is definitely enough to be able to catch it when it's dipping again. And it's actually, I wouldn't say it's better than Kepler, but we can actually tailor it to do what we want for the science on this star. Meaning that when the observation is taken, it can be analyzed immediately, and we can tell whether or not it's in a dip again. Because when it's in a dip, we can actually that's when we can get the information about what's going on, what's passing in front of it. What these dips will look like, how deep they'll be, if they're going to be periodic, anything like that. With data, with the Kepler telescope, data was collected, and every 3 months, it would point back to Earth and download the data. And so you wouldn't know until afterwards, until one of these dips were happening. And so the fact that we can get this data in real time from this network, that means that, once we see it start dipping again, we can queue up larger observatories and telescopes and get the more detailed data to figure out what's going on.
So, if there's something occluding a star's light, that thing is very large. You would think that it would get hot, and thus it might radiate its own radiation. Could we learn something about the object or the objects that are occluding the star from the radiation that they themselves emit?
Exactly. So this was actually the biggest thing that it gave us the most trouble with this star. Is that if you have any sort of surrounding dust mass or anything like that around the star, the light would hit the dust and re-radiate it in the infrared, and you would see this as an excess. And we did not detect this in any of our observations. And so a way around it was, the theory that we proposed that's still the best leading natural scenario for now is that there is a swarm of comets that's passing in front of the star. And this kind of gets around the whole infrared excess, because you would only have the excess when the material is close to the star. And comets are in somewhat eccentric orbits. And so you would have your central star here, and the comets are like this. So it's a very short amount of time that it's blocking the light of the star, and that's when you have the excess. So most of the time you're getting the, observations are out here when you can't, when it's too far away to actually, have an infrared excess. And so getting observations at all types of wavelengths will tell you, when it's dipping, will tell you, exactly what's going on, what the material is made out of.
Okay. So, I mean, for me, obviously, the most likely explanation is always just some natural phenomenon that we've never seen before. Is that where you would lay your money? And I know that we don't lay our money in science, but is that where you'd lay your money?
Yeah, I mean, I'm pretty sure everybody's on the same page. Nature is a lot more creative than we are, and it's it's a matter of time. We just we need more data to say anything more about it.
Yeah.
What would be even more awesome if we found another one similar to this, because that would make it easier to study, because then you would have a larger sample than just one.
Do you know how many Kepler stars there are? And this is sort of the only one we found like this?
Yeah, well, once we had the signal, we were able to go back through the entire Kepler data set of over 150,000 stars and search for just like the basic parameters that we're looking for. And we're able to do this down to a certain level, and we're able to say confidently, like, there's nothing down to the, when I said it dips down to 20%, we're able to make that cut at 10% and then at 5%. Below that, there's just way too many other things that stars do that get flagged in the pipeline. But Kepler only looked at a very small portion of the sky.
Sure.
And less than, a fraction of a percent, like as big as your hand is held out in front of you. Yeah. Like your fist. And so it only looked at that part of the sky. And so, new surveys coming out that are looking at millions of stars are going to, hopefully give us a new one of these, hopefully.
But I mean, 1 in 150,000 is still weird. It's a weird star.
It is definitely a weird star, yes.
And then of course, the other sort of the headlines were all about maybe an alien civilization built some kind of partial Dyson sphere to collect the energy of the sun. Are there any other super weird explanations that you've heard of? I
mean, they all pretty much go down that avenue. I do get a lot of emails from people, pretty much, a handful daily. It used to be a whole lot more. But, sharing ideas and thoughts, and some are pretty far out there. I read them all. There's no way to reply to all of them. I'm sorry. But they are all read. So the problem with the Dyson sphere idea, though, is that say you have some, very advanced civilization that's, building some sort of something to collect energy, right? Anything that uses energy puts off waste heat. And you see this in the infrared, and we do not see this in our observations. That's what gave, all the natural scenarios a very hard time for us to explain this star. And so the fact that, the Dyson sphere, scenario also requires some, infrared excess, and we don't observe that, means that it's also not a very good one, among other reasons why it's not a good one.
Right. Same goes for the potential that there's a giant interstellar space battle happening in front of the star that would be creating lots of blown up ships that could lots of all the ship debris, all those giant ships that have been destroyed, also probably would put off some heat, I would think.
Yeah, I mean, this is like, the material actually that's surrounding the star, all the shrapnel and stuff like that, that's the light would shine off of that and re-radiate in the infrared. But if you think about it, if you look at the Kepler data, and this is just fun to think about, I'm not saying it's anything, right? But there are two very big dipping regions. They're separated by about 2 years. If you assume that that's the same thing and it was some sort of, catastrophic, like, explosion, interplanetary space battle, however you want to put it, and that's the same material that's going around in orbit, then that will put the, whatever it was that got blown up in what we call the habitable zone of this star. I mean, it's just a coincidence, but it's like, it's something interesting to think about for the sci-fi folks out there. Yeah. But, that being said, the two dipping regions that, I pointed out that are very big, they look nothing like each other. Right. And so there's no reason for us to associate the two with each other, only that they're both really big. Yeah. Well, I can't wait until 20 years from now when we have all the data we want on this thing. I hope that something exciting happens sooner than that. Yeah, I'm being conservative in my estimates because I don't want to be disappointed. I mean, so like, what are your timelines for having more good data? And when you see a dipping event, what's your next procedure? What do you do when you see that something is happening to this star? You just call up all your astronomer friends and say, hey, I want you to point your telescope at this spot in the sky right now. It's very important. Pretty much, yeah. The Las Cruces Observatory, they're working with them to set up a trigger system. And so we're taking data right now. And we're using this data to find, what sort of standard deviation would be a decent limit to say, okay, once it goes below this level, this is when we need to trigger higher cadence on observations, and they could also trigger spectral observations on their network. And then we'll get notified to, send out an alert to, the bigger observatories to get, infrared data, to say, or spectral polarimetry, things to tell other things about the star. And so the timeline is we're observing it now. This Kickstarter was successful, and thanks to over 1,700 backers, we're able to observe it at least for another year. And after that, still working on a plan. Perhaps we'll do this again with maybe another twist, but we don't know when it's gonna do something again. That's so when we'll get results, and if it does something again, there is no guarantee that we'll be able to interpret it either.
Right.
And so this, it is what it is, but that will give us that much more data that we can learn from. If I go back to the two dipping regions I mentioned before, they're about 2 years apart. And the next, 2-year increment will be this spring.
Oh, okay.
And so if there were a period to that, and I'm not saying there is because they look nothing alike, but that would be, a time to, really cross your fingers and hope that it's not going to rain globally.
So my last question here for you, I think, is just why would it is very confusing to me that this would be difficult research to fund, because it got press, it's very weird, and you say high risk, high reward. I'm not sure what the risk is, except that we find out potentially, I guess, that, well, I mean, even, we're pretty sure that we're certain that it wasn't a sensor problem with Kepler or anything like that. There is something strange happening here. It seems like it would be something that a university would love to throw money at. Yeah,
well, it's funding rates these days are around 10%. And so, I mean, I've been on, review committees and whatnot. And first of all, you have to have a funding call, through NASA. They have to have a specific kind of channel that you apply through. And there is no, weird alien megastructure star channel this. And if you don't fit into, one of their channels or categories, then you're non-compliant and you can't apply. But and I've been on, these review panels, and if you're not, with a funding rate of 10%, you pretty much have to have, a project with guaranteed results.
Right.
And this, you cannot, promise anything in, the typical 3-year timeline, because, what if there's, nothing exciting that happens in that 3-year timeline?
Yeah.
Yeah, it's just not designed for that type of thing, which is unfortunate. And, it's, hopefully, someday, we'll be able to have some sort of, special channel for this kind of, high risk thing through the government agencies. That would be, because that's when you take these risks, that's when you, really get ahead of yourself, and not get ahead of yourself, but when you, when you start to, really make a difference in learning new things. Yeah. And so there should be something out there. It's going to talk to the right people to implement it. But
well, thank you very much for spending time with us, but mostly for being dedicated to this weird thing, for finding a way around the around the systems of research funding to figure out how to continue studying it, so that we can hopefully have a very cool news story to cover here on SciShow in the next few years. I think it's fantastic and really fascinating, and thanks for being a champion of this stuff.
Well, thank you for being being here for it, and keeping it real in your podcast, which was absolutely excellent, because there was some big hype.
Yeah, keep trying to find out what the heck is going on, because I cannot wrap my head around what it might possibly be, though obviously I don't know anything as much as you do. Thank you.
I bet it's going to be a non-astronomer that figures it out.
Yeah? All right.
Yeah. Because, I think there's a problem there, is that I have this bias that I know too much. It's definitely a very likely scenario that, because I say, oh, well, stars can't do that.
Yeah.
Right?
Yeah.
And then, we find the star. That's, my first reaction when I saw the star, I was like, it's bad data. Stars don't look like that.
Yeah.
And, I wouldn't have given it a second look if it wasn't for, our citizen scientists who, can do some, preliminary checks on, whether or not data is good. They said, oh, we checked this out. This is real. You should have a look. And
that is very cool. It's very cool. And I guess that's why you got to keep reading those emails.
Yep. I'm doing it.
All right. Well, thank you very much, Tabetha, for joining us and for doing really cool science. It's a pleasure to have you.
Thank you, Hank.
Just one human genome, and it took hundreds of people many years to read it, and it wasn't even a very good version.